of temperature on the rate of reaction. The Arrhenius equation, which gives a satisfactory explanation on the concept. The Arrhenius equation says rate of reaction is a function of energy of activation and temperature, or rate constant or rate of reaction is a function of energy of activation and temperature. So this equation says higher the value of energy of activation, higher the value of EA, lower is the rate, and vice versa. Or higher the temperature, higher the rate of reaction, and vice versa. So this concept gives an empirical relation between the rate constant or rate of reaction between energy of activation and temperature. As you know, in the reacting system, there is always a barrier, that is energy barrier. So this Arrhenius says there is always energy barrier in the reacting system. And those reactant molecules which can able to gain this energy, that is energy of activation, can have the chemical change. And the reactant molecules will remain in the reactant state as long as they are unable to gain this energy of activation. The moment they gain, they change into product. That is what the Arrhenius says. From this concept, we can give the reason for, that is to our doubts. That is, one is the rate of different reaction. I mean, we have different reactions, inorganic reactions, organic reactions, biological reactions. Different reactions have different rates at same temperature, room temperature or some other temperature. Different reactions have different rates. The reason here, that is A, energy of activation. It is specific. It is different for different reactions. So lower the value, that is lower the barrier, easy to cross over, faster the reaction. Higher the value, that is height is more, that is difficult to cross over, lower the rate. That is why different reactions have different rates at same temperature. That is the answer. We get it from this equation. And one more, temperature. Temperature means same reaction. If you take one reaction, one particular reaction, same reaction will have different rates at different temperatures. In endothermic reaction, the rate increases upon increasing temperature. That is, upon increasing temperature, rate increases. But energy of activation remains same. Why? What does the rise in temperature? It is, that is actually in the rise, that is when you rise the temperature, thermal energy content of the reacting system is more. We are supplying energy to the reacting system in the form of heat. Heat is a form of energy. So more energy content in the system, the reactant molecules can quickly gain the energy, and more fraction of molecules can cross over the barrier. That is why rate becomes higher at higher rate of temperature. As the temperature increases, reactant molecules can more and more quickly gain energy, and fraction of molecules can cross over the energy barrier becomes more and more. That is the reason same reaction will have higher rates at higher temperature. So that is the explanation we see from this Arrhenius equation. Why different reactions have different rates at same temperature, and the same reaction will have different rate at different temperature. There is one more concept is there on the energy of activation, that is the effect of catalyst. Look at this energy barrier. we have two different types of catalyst. Catalyst means which can either enhance the reaction or what is it, enhance the rate of reaction. The catalyst which can increase the rate of reaction, a positive catalyst, or a catalyst which can decrease the rate of reaction, negative catalyst. Both are possible. In this case, the presence of catalyst means catalyst molecules in the reacting system, very few required. That is, very small amount of catalyst is sufficient to, that is, change the entire amount of the reaction. Those catalyst molecules interact with the reactant molecules in such a way that is produces some kind of state in which the energy of activation for the reaction it is decreases. So reactant molecules can gain, need not gain this amount of energy. The reactant molecules can gain energy less than what is expected. That is, crossover is easy. More molecule can easily cross over, lowering of barrier, presence of catalyst. That is why rate of reaction enhances. Same temperature, same reaction, presence of catalyst will increase the rate of reaction. That is a kind of interaction between the catalyst molecules and reactant molecules. That interaction will have kind of some state, that is entirely different state, which require what is not this amount of energy of activation, less energy of activation. Yeah. That is one case. In other case, a negative effect. There are catalysts which have what is that opposite effect. That is a kind of interaction between the catalyst molecules and reactant molecules, which produces a state which can increase the energy of activation or energy barrier. That interaction produces some kind of state which requires more energy of activation. So that is why rate of reaction decreases here. Examples for the negative catalyst we see in our daily life, that is a preservative. Using preservatives and foodstuffs, packaging of food, that is packed food. We put some what is a preservative, the food which may be in the liquid state or solid state. Liquid state may be fruit juices like that. As you know, the foodstuff major content is the proteins, carbohydrates and fats. These are quite a big molecules, macromolecules, which decompose by the action of microbes, that is bacterial decomposition, or by the action of oxygen, that is oxidative degradation, by the action of water, hydrolytic degradation. The molecules get degraded by this activity. So it is a natural process, by themselves it occurs. But that process is a chemical process which can be prevented or that is rate of reaction greatly decrease by adding negative catalyst, that is a suitable preservatives, some organic compounds you are preparing, that is. So that what is that will have a negative catalyst, that is why it will reduce the presence of preservatives, will reduce what is that the rate of decomposition of these what is that components, thereby increase the lifespan of this food. So packaging of food, always we apply preservatives to preserve the food for a longer time. So effect of catalyst on the energy of activation. So all these concepts, what is that requires energy of activation, or Arrhenius what is the theory to explain what is the rate of reaction in terms of energy of activation, in terms of temperature, or the effect of catalyst. And one more equation we need to understand. This is one, as you know, that is a temperature coefficient of reaction. What is temperature coefficient of reaction? Temperature coefficient of reaction, most probably it may be either 2 or 3. 2 means rate of reaction doubles for every rise in temperature, every rise in 10 degree temperature, very important. Every rise of 10 degree temperature coefficient. So 3 means Rate of reaction triples for every rise in 10-degree rise in temperature. That is the meaning of temperature coefficient of reaction definition. Temperature coefficient is either a chemical reaction. In most of the cases it is a 1, it is applicable, and very rarely this 3 is possible. That is, rate of the reaction is almost double by every rise of 10-degree rise in temperature. That is called temperature coefficient. That is why we have set this equation. This is a rate of reaction when the temperature rise, delta T rise in temperature, final temperature minus initial temperature divided by T. C is the temperature coefficient value, maybe 2 or 3. So it is a rate before the rise of temperature. R2, R1 different in rate. That is why accordingly we can calculate the rate of reaction. That is, for C equals to, you have done the calculation, the problems are set for C as well as for these problems. For C equals to, that is, when the temperature coefficient of the reaction is 2, reaction doubles for every 10-degree rise in temperature. Let us see what are the possible equations. That is, C equals to, for 10-degree rise, that is delta T equals 10, 10 by 10 equals 1, that is 2 to the power of 1. R2 equals cross multiply 2 into R1, 2 to the power of 1 means 2 into R1 for delta T equals 10. So rate of reaction doubles for 10-degree rise in temperature. When the temperature rise is 20 degree, same equation. C is 2 for this one. Delta T, that is 20 by 10. Increase in temperature 20 by 10, 2 to the power of 2, that is 4 times. The rate of reaction increase by 4 times for R2 is equal to 4 into R1. The rate of the reaction increase by 4-fold for a rise of 20 degree in temperature when the reaction have the temperature coefficient 2. That is the one. That is general equations. Similarly, we have for 30 degree rise in temperature, that is 3 to the power of 3, that is 30 by 10, 3. That is 2 to the power of 3 is 8. 8 times increase in rate of temperature for a rise of 30 degrees centigrade, 30 degree rise in temperature. Suppose a fraction like this 25 degree, 15 degree or 32 degree. What is the rise in same equation you can apply? R2 is equal to, for 25 rise in temperature, 25 divided by 10, 2.5. So 2 to the power of 2.5, do the mathematical calculation, 5.657 into R1. Rate of the reaction increased by 5.657 times the rate of reaction, initial rate. That is the increase in rate of reaction. This is for C equals 2. Similarly, let us see for C equals 3. That is the rate of reaction triples for every rise in temperature, very rare cases. Do the same equation. That is C equals 3 in all cases. For 10 degree, 3 to the power of 1, 20 degree, 3 to the power of 2, and 30 degree, 3 to the power of 3. That is, C is 3, 3 to the power of 3. C in this case, 3 to the power of 3, that is 27. So for 10 degree, it is 3 times the rate of reaction. For 20 degree rise in temperature, 9 times the rate of reaction, increase the 9 times. For 30 degree rise in temperature, the rate of reaction increased by 27 times if the temperature coefficient is 3. That is the calculation. So that is one separate example. For any fractional value, that is temperature rise is 15 degree, 15 by 10 is 1.5, 3 to the power of 1.5, 3 to the power of 1.5 is 5 point, this is the value. Rate of the reaction increased by this times the R1 for an increase in temperature 15 degree when the temperature coefficient is 3. That is a general calculation. You can set, they can set any number of problems on like this. So I have worked out on problems of this. I am taking the rate of reaction as 2 into 10 to the power of minus 6 moles per second, molar per second. The rate of reaction is 1. Let us calculate the rate of reaction for like this now, for this case only. Let us calculate the rate of reaction for this one, and this one. Do the same problem. R2 is equal to 2R1 for 10 degree rise in temperature. R2 is equal to, is a rate, 4 into 10 to the power of minus 6 molar per second. That is for a given value. That is generalization. Similarly for second one, rate of reaction increased by 4-fold. If R1 is this, rate of reaction is this. Similarly 3-1, rate of reaction, that is increased by what is that? 8 times, for an increase of what is that? 30 degree centigrade. Yeah. So it becomes, this is our R1, this becomes R2. So rate of reaction is this value. For a fractional value, that is 2.5 to the bits, that is for a rise of 25 degree centigrade, this is the rate of reaction. This is, take an example as the rate of reaction at one temperature and other temperature is the rate of reaction. When the rise in temperature 10 degree, 20 degree, 30 degree and 25 degree. Similarly, we have calculation for this rate of reaction for C equals 3. Let R1 is equal to 4 into 10 to the power of minus 3 molar per second. M stands for molar, change in concentration. We do the similar calculation for this, for C equals 3. 3 into this rate. For this, for rise, for 10 degree rise in temperature. Suppose 20 degree rise in temperature, 9 into this. That is 9, 4s are 36. For 30 degree rise in temperature, 27 to this. For 15 degree rise in temperature, this into this. So R2 is equal to this times what is, this is the rate of reaction. So this is a sample of problems. What is that? Can get any number of problems they can set. Knowing the rate at one temperature, we can calculate the rate at other temperature if the temperature coefficient is given, either 2 or 3. And the last problem, using the last equation, last time I have calculated the energy of activation using the same equation. That is the one, the problem is that same equation, Arrhenius equation, finds application here also. If you know the rate constant of reaction at one temperature, we can able to calculate the rate constant of the same reaction at some other temperature. Rate constant at this temperature. What is the rate constant at this temperature? Given the energy of activation, it is important. If you know the energy of activation, that is kilojoules per mole, 40 kilojoules. Kilo means 10 to the power of 3 joules per mole. So if you know this same equation, that is same equation is rewritten like this for different two values. Recall the last class formula. Log of K2 is equal to K2 by K1 is equal to. So K1 is rate constant at temperature T1. K2 is a rate constant at temperature T2, energy of activation, or is a gas constant. Substitute the given values. That is, energy of activation is 40. Don't write in Kelvin, joules per mole as I write. That is, kilo means 10 to the power of 3. 320 minus 300, that is 20 difference. And that is R value 3.303 into 300 and 320. Simplify. This cancels zeros remaining here. That is, divide this, multiply it and divide this by this. Use 0.4. That is logarithm of K2 by K1 is equal to this. So eliminate log. You can eliminate log taking anti-log on both sides. Anti-log of log means cancel. This is K2 by 1 and anti-log of this. Find the anti-log. That is, anti-log is 2.724. Anti-log of this, that is, anti-logarithm table is there. Look at the table and calculate what is the anti-log of this. K2 by K1 equals this. What is K2? This into K1 is given like this. Multiply. That gives the value of K2. That is 8 point this So 172 into 10 minus 5 per second. That is the rate constant at temperature 322. This is how we can calculate the rate constant. There is another application of Arrhenius equation. If you know the rate constant at room temperature, we can calculate the rate constant of the same reaction at any temperature. That is the point. Thank you.